So, we're gonna start doing the, thank you, Mom. So we're gonna start doing the effective potential derivation for general relativity. And then, we'll get that primarily done today, and then on Friday, we will then do the rest of the order equation. The perception of the perihelion and Mercury. It's not hard, but it's one of those where it's an approximation to an approximation, and there's a little bit to it. Not hard, but it's very questy. Okay, so let's talk about the GR of 1/2 u r dot squared plus g of r equals e. Okay, so we had that problem when we did the Newtonian classical mechanics. And we're going to get basically the equivalent of this expression. So we're going to start. So we start with our buddy the metric. Oh, I'm just waiting on the one. So we have that expression there. And the way we're going to start off, we're going to first of all look at for isometries. Okay, we see there's two. We can see that if we were to take the partial of all the J mu components here with respect to T, that equals 0. Okay. And then also if we do this right here, with respect to phi, we know that this is also 0.
That's our isometries.
These are the isometries. So what we're going to do, I'm going to call this Killing factor K mu, and this is going to be 1, 0, 0, 0. And this one here, I'm just going to call something else. I'm going to call eta just to distinguish it. And so this Killing vector. And what we did when we went through that derivation, I'm just going to state the result. Well, we went through and showed that if we have this here, I meant that this K mu P mu. So we'll have the eta mu P mu as a constant. And we showed before that this one's going to be connected with energy, this one's going to be connected with angular momentum along the z-axis. So let's go through and do it again. Okay, so let's look at our K mu. So K mu P mu. Okay. And this one here, if I put in my buddy K here, this is just going to be P0. And P0 is Gupu.
Not this again.
Or Gupo. So what do we know about Gupo? Okay, well, unlocked. Okay, we know that Gupo has the name 1 minus RS over R. Okay, that's Gu. Okay, and what is Po? Po is, remember our P mu here.
Yeah,
This P mu is going to be our M U mu. Like that. Okay, and so this one here is going to be what? It's going to be M dt d tau. Okay, and we know that this is a constant. The factors of c squared all being neglected here and all over the place and blah blah blah. I'd like saying blah blah blah. Now that's a constant. So if I go really far away, in other words, if I let r go to infinity, and if I take the object to be at rest, what is this going to equal then? This term goes to 0 here, and this the tau becomes t if I'm far away, and so this whole thing here just becomes -10. Okay. And this is just nothing with factors of c. Remember, we're in natural units here. So this is the same thing as saying minus e. Right? Because it'd be the mc squared. And so I kill all the minus signs, I solve for my buddy e. So my buddy e is 1 minus rs over r m dt d tau. I'm gonna take over my little m here. I'm gonna write this as little m over, E over m. It's gonna be 1 minus rs over r, dt d tau. So this is an energy for units.
Did we show that it has to be negative E for negative M?
Well, if r becomes large, this goes out.
Oh,
Okay,
yeah.
so you get the minus out here, and this goes to 1. This energy for units. So that's our one little thing here. Amelia, I'm gonna write that equation in the phantom zone.
Phantom zone for once. There it is. I hope no nefarious things are written in that.
Well, this is very general audit, so you have to. I hope he doesn't come back and try to close you out. Okay, so that's good to know. Okay. Okay, so we have that. Now let's do the exact same thing then for our eta buddy. So repeat. For eta. So now we have, yeah, think about it. Yep.
Do we want to rewrite dt d tau as gamma?
No, we're gonna leave it like that.
Okay.
Can't wait to find out why.
It looks weird because it's supposed to be a constant for both of them.
The whole combination is a constant.
Yeah,
Okay.
but we're having a change or something.
So, we're just gonna leave it like that because it's gonna give us something we want. Can't wait to find out what that is. Okay. What are we doing? We're doing this. Okay, so this is eta mu p. Okay. That does look like your pen. Which actually we had in classical Greek today. It's metanoia, which means change your mind is what repent actually means. Okay, so. Good to know. So what does this become? This becomes P.
Three, yeah, I was
Okay.
trying to figure out the in there.
And so this is gonna be. This is pronounced Gree 3, okay?
Got it.
Okay. Yeah. So what is G through 3?
R squared.
Yeah, so this becomes R squared sine squared of theta, okay? And then this guy becomes M. What would be U3 then? In this metric? D phi.
Tau.
D phi. D2. D tau.
It's
D tau. Yep.
just to make sure my mathematical understanding is correct, gamma is equal to dt over d tau. Like if you work it out, it will be the exact same.
Correct. Yeah.
Because t equals gamma d tau, so d tau over d tau 1 and then gamma.
So we have this. Now, what we're gonna do is, again, remember, we want to basically look at the corresponding equation in GR. And so in classical mechanics, what was our theta?
90?
90 degrees. So we're gonna left. Theta equal 90 degrees.
Why was it 90? Because the sine squared was 1.
Yeah, we want that to go to 1 because we want to be in the XY plane.
Oh, I forget that it is from.
Yep.
Yeah.
And this is the constant. So we put this all in here, we get R, we get MR squared, okay? D phi dt, d phi d tau equals. Well, MR squared is our
Moment.
moment of inertia, d phi dt, d tau is our angular velocity, kind of properly understood. So what would be a good name for this? The angular momentum about the z-axis. I'm just gonna call it L.
Why is it about the z-axis in this case? Is it because we're
Because,
in the x, y?
yeah,
plane,
because
so
here's
it's-
our x, y, z, this is z, this is x, this is y. And then if here's my r, the r goes from here. And we basically let theta equal 90 degrees, so it's in the x, y plane. Okay. And
So whenever it moves, the actual momentum is this.
Correct, yep.
Back to left.
Yep.
So the moment of inertia isn't that for just a sphere, mr squared?
Short point, yes.
For a point?
Yep.
Okay, so, because moment of inertia could be totally different for different.
Well, the
bodies.
moment of inertia actually ends up becoming a second rate tensor.
Mhm.
Okay, it becomes this really hellacious thing to calculate.
Okay. But I'm just trying to justify how we're putting an L over there.
Well, because we know that this is your I, right? The I for, yes. Okay, this right here is your omega here, and that is the definition of what it means to be angular.
But we're gonna be applying it not only to point particles.
No, right now, we want the orbit equation for a point, just like what we did with the mass going around the sun.
Oh, that was just.
We
a point
want,
mass.
yes, we want the corresponding here.
Okay, got it, so it works.
So I'm gonna take this over here, so this is gonna be the R squared dp d tau equals L over M, and this is your angular momentum per unit mass. Okay, so what we're gonna do now is that goes to the phantom zone.
And zone you are, the more you can see.
Yeah, I drew the line terribly, but
Because our space is curved.
it's true. The angle of the camera makes the space curved.
Now, what you might think to do is you might want to think, well, we can find the geodesics for this and then actually solve those equations. Because how would a planet move it follow the geodesic? And that's correct. The problem is that the geodesic equation is actually straight from hell. It's like a singular, oh, no. So instead, we're going to use a trick.
Wait, so you're saying without these, we could start with geodesic
Yeah,
equation?
well, you could think, well, why are we going through all this here? Why don't we just start with the metric, from that find the geodesic equations, because that's going to have to be the path that a planet takes, and that's completely correct. Okay, but the
But-
problem is that those equations are really, really hard to solve.
We also have the d by dt and dt d tau, right? So we could plug.
Well, we
it
have
into-
them here, but we don't have them.
Could we plug them into the?
We're gonna plug, you can put them in there, and that helps a lot.
Mhm.
Okay, but it's still you have to, it still becomes actually quite nasty.
Because you still have
You're right,
Christoffel
Eric.
symbols in there.
Yeah, I mean, it's still, well, we know what that would be. We have all those worked out, but the radio equation turned out to be really, really hard to do.
Okay.
There's an easier way to do it. So. The radio geodesic equation. From the S squared is a complicated mess, a complicated equation.
It is ew.
Okay. An easier approach. Is to look. Is to use u mu. Okay. What do you know about u mu?
Lawrence
It
Taylor.
was t something times the r times the.
Okay, so what is this? This is really the dx mu d tau. Dx mu d tau. Okay. So. I remember what that ends up being?
I think it's the t00 or rho naught, no?
No, this ends up equaling minus c squared. But in natural units, this ends up being -1 for a particle of mass. But for light, what does that equal? Yeah, what is this part here? dx mu is ds
Just
squared.
So that's.
So what is ds squared for light?
Zero.
0. Is for light, 0. What I'm gonna do is I'm gonna say u mu is gonna equal, I'll say minus epsilon. Where epsilon is 1 for man. 0 for light. Maybe I should call it delta to make it look a little more 1 over 0 light.
Wait,
We can do whatever you want. It's your course time.
Okay. The course belongs to the ages.
Oh,
So what do we have for this? Let's crank this out. So this is gonna be, this is G, so u mu is G mu nu. U mu u nu. And this is equal to minus epsilon. So if I put this all in here, we know that this is diagonal, so we're only going to get diagonal elements here. So this whole thing reduces to mu. I can't even pronounce that. Gu. Okay. Plus G11 U11 plus G22 U22 plus G33 U33 equals minus epsilon. Now, what is this guy here? This is going to become minus 1 minus RS over R. Okay, and this fellow here becomes dt d tau quantity squared. If only we had a dt d tau someplace. Thank you. Plus, what is my buddy here? My buddy here was 1 minus RS over R. This is dr d tau. Plus, what happens to this from here? Right, this would become r squared d theta d tau squared. But what do we know about theta? Theta is 90 degrees, so
constant.
it's a constant, so is
Zero.
that is 0. This theta is 90 degrees. And plus this one is going to be then r squared sine squared of theta, but again, that's going to be 1 because theta is 90 degrees. Okay, d phi d tau squared equals minus epsilon. So what I'm going to do is,
I think you
well,
made a transcription error in whatever you erased, but it's gone now, so whatever.
That's fine.
I don't know what you're thinking about.
okay, so what I'm going to do is I'm going to multiply by one minus RS over R and sub n for dt d tau and d phi d tau. Okay. And if we do this, what does this give us? This gives us 1 minus RS over R comes in squared, because I'm going to plot through by this fellow. By dt d tau from the phantom zone is my buddy over here. Plus, I multiply through by this factor, so that fellow's killed. He's out of there. My buddy over here, if I solve for that. First of all, I had this term gets multiplied by the 1 minus RS over. Then my buddy over here gets split. And my buddy over here gets multiplied by 1 minus RS over R. Clearly that one. Okay, it did. Okay, so this factor here cancels that factor here. And I'm going to take this factor to the other side. Okay, so this gives me minus E over N, 1 2 squared, that's really simplified, plus dr d tau, plus, okay, I'm going to take this term over here, I'm going to factor out the 1 minus RS over R. So if I take this over here and factor out that term, what am I left with? I'm left with this times this, and you can see there's some simplification here. This will leave me with 1 over R squared, L over M squared like that. Right, because this comes in squared, this goes to the fourth, so that gives me this term. And if I put this over here, this gives me then plus epsilon. Does everyone agree?
Yes.
Now, recall. We would like an equation. Like 1/mu r dot squared plus this v effective equaling. First of all, I don't have to worry about this mu. How come? Because I'm having these things like per unit mass. So I'm not gonna worry about this mu. I can always just divide through by this mu and I can have something I have like an r dot squared. This looks like an r dot squared, but what is missing? A half. So I can multiply everything through by a half, just so I have a term that has 1/2 and it's something that looks like r dot squared. That's the only reason I'm doing that. Okay?
Oh, with E, we already have that, but why is everything squared though? Like our E is not squared.
Correct. There's gonna be some reinterpretation.
Um,
It's a new theory, so we're gonna get new results.
Nice. I just was like, well, it's not working out, so.
Well, I don't know if he did it this way. He may have, I don't know. I'm just doing the way that I'm just taught. I do nothing original. I'm just teaching you basically it's like a vampire. You know, how do you get a vampire? Well, you're human, then you're made into a vampire. And then you make other vampires. So I'm just doing the same thing. I've learned something, I'm just passing it on to you.
It's your educational vampire.
Exactly.
I don't know if that's a good synonym for a professor.
In the grand scheme of things, would you rather be a vampire or a werewolf? This is a profound question. And I think I'd definitely go on the werewolf side.
Yeah, no, we're.
Because
You're a
the vampire, first of all, is just way too serious. Okay, way too
You
serious.
can't go outside during the day.
Yeah,
love that.
and they're solitary.
Too.
They're solitary too. They're just way too serious and solitary. And I'd rather hang out with my buddies. You know, what do we do? Go out in the woods, get venison. You know, about once a month.
Nice.
Yeah,
Sounds like a
yeah,
nice life.
yeah. You have to get a lot of clothes, but you know.
Well, I mean,
Okay.
if you know when the full moon's gonna be, run.
Yeah. Yes.
If we wanted to look like the 1/2 yada yada equals E,
Mhm.
and we have an E squared, should we multiply by a quarter then?
No, we're gonna just redefine. We're gonna have some redefinitions here. Okay. So if I do that, I'm gonna start off with this term first. To be deep. I'm gonna have a plus 1/2. All this other stuff here, I'm gonna multiply this stuff out here. So I'm gonna get this times this. And this and this,
I mean, if that part equals 0, then.
and this and this. And this and this. That, and then I'm gonna take the other term to the other side. Okay, what am I gonna call this whole thing here?
Be effective
This
or
might be effective. What am I gonna call this? This guy here, but I'm gonna give a different symbol, the symbol that Carol uses, he uses scripting. Ugh.
oh, of course.
Okay, there, now,
Wait, what happened to the M? Because we had the E over it.
the E over M, this over here, thank you, yeah, like that, keep me honest.
I didn't know that had just disappeared or.
No, it's just me being stupid. That makes sense? Now, what do we have here? For matter, our epsilon is 1. So for matter. Epsilon equals 1. So now I'm going to rewrite that equation with a 1 in here.
This equals C squared.
Well,
It's C squared, right? Epsilon for matter.
yeah, but not in natural units, it's 1 or 0. So. After a while, you realize the genius of natural units. 1.
I still am.
I want to leave it.
Yeah, I mean, even if you're a natural units, like when you go to calculate something, you still have to put those C's in there, right?
Yeah, when you actually go to calculate, you actually, because they have to convert it to units we use. And so at some point you do have to restore, if your G is one, because sometimes people take G to one.
And
Sometimes even the capital M is set to one, they'll take units of G times capital M equaling one. You have to at some point restore everything.
so how do you do that?
You have to figure out what factors you need to get the right units.
Oh,
Since you just dropped those factors, it's just multiplicative.
and,
Is this actually an effective potential, or are we just
We're-
defining it?
We're
as-
defining it as effective. Plus one minus R squared over R cubed. V squared. Oh, actually, damn it.
You mean, is that an N, not a 3?
Okay, well, that's what I can do here. Yeah, I have no idea how the hell that three got in there, but watch what I'm doing, since I have the magic power of finger. Okay. Also, what I'm gonna do is that this one here, and I take to the other side. Okay, so what I call it the effective, should have really done. Okay.
Time to scribble this shit out.
So if I take the epsilon to the other side, this gives me minus, remember the epsilon is one,
Minus 1/2.
so this becomes minus a half, and this whole thing here, I'm gonna call strip D. Or it's basically, I don't know. Okay, but then it doesn't, then it's not here,
So get rid of the 1 and the.
so actually it should be up here. Okay, something else, this would be,
That's cool.
Yeah, that's gone.
Just like that.
And then just add the
Then-
epsilon to the other side. So
then
there's 1/2
this will
epsilon.
then become our here, this guy. Then strip D.
Is the set?
and I don't think you have that plus one
Yeah,
in
that
there.
plus one.
The term after that, I think should be an R cubed, not a. Yeah. That's actually where the 3 came from before.
That's actually gonna be the new physics term. Okay. Now, if I, let's go through and restore the actual, our RS, and what did we say RS is?
2 GM.
2GM.
Over C squared, but
That's gone. Okay, so if we actually go through and restore this stuff, this gives me 1/2. You already tell. Squared plus I'm gonna put in these terms in originally. This will give me L squared over, like this. L of M. Squared over 2R squared. You'll see why I'm writing this for a second. If I put in my 2GM in here for this, the 2 here cancels, and so this gives me the GM R cubed. L of M squared. And then this term here, again, the 2 cancels, this gives me minus G M over R equals this. Now compare this to our V effective here. Our V effective compared to the Newtonian. Okay, so what was the Newtonian case? We had this L squared over 2 mu R squared, right?
yeah,
Okay.
yeah, minus the,
And minus this G big M, actually. M1, M2. Actually, yeah, we call it here, over. R, that's what we had before. Now, in our case here, what would happen here, one of these would become capital. Right? Let's say that one becomes capital. And what happens to this, and this would also be divided by,
multiplied by that.
did we have, and I think we just had it like that, didn't we?
Yeah.
Yeah, okay. So how does this compare with this? It's actually a great comparison here. So first of all, here we don't have, remember, we don't have a mu in here when we do this case here. So we don't have this mu here, you know, in general relativity. And we have an L over M
Yeah.
here. So this term here is really this term here. It's the 1 over R squared. So this term is just this term here. This term is really this term over here. Again, what we have is that we have a capital M here. We don't have this little mass here going around because of how we we did this. So that guy doesn't exist. But this term is that term here. Okay,
Oh, so our L's become L over M?
yeah, or that actually has an E over M in it as well. Okay,
Yeah, okay, got it.
which we're not gonna. So, this right here is a new term. Okay, so what happens is, the minus GM over R cubed, L over M squared is new to GR. So this is actually a new term. And that's ultimately what's gonna, it turns out to be a small term. We'll just have to compare it to some stuff here. Once you restore units and stuff, this is gonna become a small term here, which is ultimately why, we're gonna find out that this is gonna cause the first section. Okay, that makes sense? Okay, questions? Okay, so now let's look at this. Also recall. In Newtonian. The Newtonian case. When we looked at this to be effective here. Versus R, what did we find? We had this piece here. This is R minus G M1 M2 over R. That was not that at all. This is the L squared over the R squared term. And then we have this term here. And this is our minus G M1 M2 over R term. And we said that we ended up with this one here. So what's going to happen in our case?
We'll have a third.
These two terms are going to be more or less the same. So we're going to get something like that. But what's this term going to do?
Decrease. Sorry.
As you get really, really small r, what happens here? This term is going to dominate.
Yeah,
Okay, it's going to dominate badly. So what's going to happen here when you put this together? We plot the effect with here. Versus R. What we're going to find here, they're going to get something that looks like. This becomes small. It's going to look a little bit like what we have. It's going to look a little bit like this barrier here. Okay, then you're going to get something that goes like that. And there's a really nice graph of it.
so it's now
Okay.
above the.
I mean, it's going to depend a lot on what the L value is and stuff like this. Okay, there's a nice graph of it on the new handout I gave you. If you look at page 195, so in other words, flip the page. Yeah, they actually have a nice little. Actually, I didn't give you justice here. I should have done. Let me do a better job. Then. So what does he do? He puts in the Newtonian case here. So here's your Newtonian case.
Oh, he's plotting it R over N as well.
Yeah, we're not gonna worry about that. That's just factor. Okay. And then if you put this guy in here, you're gonna get something that looks like. Then it matches like this. And what's gonna happen if the R becomes large, this term becomes small. Okay. There's gonna be something like this, and this drip here. Okay, good. This dip here like that, what's causing that is this term here, which is negative, that's going as 1 over R cubed. So there's gonna be already, you can see one difference here. In this case here, no matter what the energy is, you always have a turning point.
Yeah.
Yeah, you always have a turning point here. In this case here, depending on where your energy is, you have a turning point. Now, if you go over this barrier now, you don't have a turning point.
So you're,
What's gonna happen, you're gonna go right into the black hole no matter what. Okay, you're stuck.
and that means that, wait, that's the effect, so if that's our energy, so we have a higher energy, orbiting that thing.
If the energy is high enough, okay, it's not gonna see this barrier at all, and you're gonna go straight into the center. Okay. We're gonna have a more complicated feature here. Now we can do a couple of things here. We said if we're down here. what do we get? We get an ellipse here. Okay, we went through and did this here. What do we have the corresponding thing here?
Will also be an ellipse? Oh, no.
Well, I could have something here.
There's
What do you
three
have to
intersections.
If I could have something here, I'd have this turning point, I'd have that turning point.
And there's a third one.
Okay. And how would I go about finding that? Suppose I want to find that point.
You just solve for V effective, no, or for R, because you know your E.
Yeah, so what would have to happen here? The V effective would have to be what?
E.
Yeah, just the V effective would have to be this script here like that. Okay. And you can actually solve for that value there. Okay, so you can find those 2 points here. Now, what about circular orbits here? Where do circular orbits? Let's guess here. The circular orbit occurs
At the bottom.
right here. This is a circular orbit. Where do we get circular orbits here?
No, we always have two intersections at minimum, right? So.
Okay, what happened to this circular orbit here? Why was this a circular orbit? Because we looked at this partial would be effective with respect to R. What does that equal there?
Zero.
Equals 0. Do you have something corresponding to that here?
Yeah.
You have a top one. You have one here. We also have one down here. So we have 2 circular orbits. Let's actually calculate those. How do you calculate those?
Take the derivative, set to zero.
You take the derivative and set it to 0. So let's see what we get.
What they say.
So let's take the derivative of this guy. Okay, so if I take the derivative of this is gonna be, so the derivative will be effective. with respect to R equals what? Oh, this is gonna be this is R to the minus 2 power, so this will be minus L over M squared over R cubed. Right? And this piece here gives me what? This will give me, this is an R to the minus 3 power. So this will give me 3.
Do we want to include that path and stuff, or?
It's zero, right? So we're setting.
What do you mean?
Oh,
I'm saying this whole thing here is your V effective.
right, there's the two.
Yeah, so when you take, this is R to the minus 2 power. So when you take the derivative, minus 2 comes out.
Oh,
Equal to the-
yeah,
Okay.
yeah.
That's fine. So this is R to the minus 3. I pull that out. That'll be give me a 3 GM over R to the 4th L over M squared. If I do this one here, this is R to the minus 1 power, so this is going to be plus GM over R squared. And that has to equal 0. Now, what I'm going to do is I'm going to multiply everything there by R to the 4th. So multiply everything through by R to the 4th. This gives me minus L over M squared bar. This term here just gives me plus 3 GM L over M squared. And this term here gives me plus GM R squared equals 0. And that's just nothing but a
Forward.
that's just a standard
What?
quadratic equation.
Oh.
So that was on a surface. Okay.
I just realized how interesting this is gonna be when you work it out with a light case.
The light case will be, fortunately, I had to erase that because there's not enough room there. So there is enough room in Owen. Okay, so, what does this give me? Minus B, which is,
3 GM, or nope.
try again,
Yeah, that's the L over M,
give me this term here, so this is L over M quantities,
but
plus or minus the square root. Of L over M, the 4th power.
that's where you get us smarter in the America. We do that so in 2 steps, but you just do it in one. Cold War one.
What other stuff do you do?
Like we calculate the discriminant first and then just do a square root of D.
At least you know the word discriminant.
Yeah.
The word discriminant is even used in anymore. How about
It's just in
Manchester?
my school.
Not in high school.
Yeah.
I never.
Yeah, I mean,
even
my,
encountered
that's, well, I guess one of the only good things my school did though.
it.
Okay, plus, 4, I'm sorry, minus
Or,
minus 4 AC, so our A is
Wow.
here, our C is buddy here. All over 2A.
That's what you would have guessed.
Pretty obvious if you stop and think about it.
isn't our A GM?
What is that?
Well,
yeah, I don't- I don't think that's right.
4G?
6.
Minus 4G,
Oh,
this is, this is.
Yeah, on the bottom. To A, not to B.
Oh, yeah,
Oh.
thank you, no, keep me honest. 2G. Okay. So I'm gonna pull out a L squared over M to the 4th power. If I do that, it's gonna be squared. And so this is gonna be R equals L over M squared plus or minus L over M squared, square root of 1 minus, so we get a 12, a G big M squared here. This will give me M over L squared here like that, all over 2GM. That makes sense?
That looks good.
I think I see
Yes.
one of the cases is going, I don't see the other one.
Now, any questions about? So now we have 2 cases here. We have the R plus, which is gonna become L squared. I'll just factor out this guy. I think 1 plus the square root.
You still need a square on that, right?
Well. Okay. 1 minus 12 GM squared. Another one L squared. Okay. Now I'll pull up this guy here.
So the two M's are different.
Correct. That's one of them. Okay, then the other ones are the minus. So that's what those two values are here.
Or you would have guessed that.
Yes. What else could it be? Duh, come on. That makes sense?
Yep.
So that's what those 2 extremes are. Now, if you look at that picture though. When we looked at this guy here, we had this. And this one. And this one, they're actually different. Okay. So this one here is going to be the R minus, because it's closer. This one here is going to become R plus. Okay. What do you notice about these? Let's say this one here, let's see this. If this one gets pushed a little bit this way or this way, or this one gets pushed this way or this way, what's the difference there? One is actually going to be stable, the other one will not be stable. Okay, this one here, you can see what happens here. Remember that if you look at the derivative of this guy here, when this is like this, these are stable positions, these are unstable positions. Okay, so this is unstable. Remember, because your force is given by this guy here. Okay, and so when you have a case like this, if you look at the slope, this would be a negative slope with a minus sign to make the force go this way.
Yeah.
There's this one here. This is a positive slope, so I need to displace one this way, push this way. So this is unstable. So that's gonna be unstable circular motion. This one here is gonna be stable circular.
So like, if the top position gets pushed from its location, it's gonna leave that circular orbit.
Correct.
And
Yeah.
but that one would try to get back to.
Yeah. That'd be stable. Yeah. Okay. That makes sense.
But where? I'm trying to think of like physically where this radius is.
Wait, yeah, is that saying that there is only one,
Stable circular
Stable.
orbit around it in the short shell metric.
there's
Stable
just
cir-
one?
Stable circular orbit.
Given an angular momentum, mass, etc.
Okay, so if you had a bunch of planets orbiting, only one of them could be perfectly circular, the rest of them
Well-
would be slightly elliptical.
Depends on what the L is, depends on what these values are here.
Yeah, mass.
So depending on what this L is and.
If they're the same mass, then yeah, alright, there's a
Because
number.
they're different system.
Okay. Now, what happens if I evaluate this at the short shell metric? Right, I'm gonna regret. This is Bad. This is bad.
I mean, you have the plus and minus right there.
We also have about a minute.
Yeah, clock is against me, and it was against me last time too. It's always against me, it was against me in all my classes. Therefore, I must destroy the clock. The clock is the enemy. Okay, so we have this be effective. What the hell was it again? It was this L over M squared. Well, okay. We will see. That be effective. At R equals RS equals 0. Okay, so what's gonna happen here is at this point here. That's gonna be your, that'll be your short shell radius. You're gonna see that.
So why is there an orbit outside of it that's unstable?
This is a whole new prediction from the relativity. Okay, it's a whole new result. Okay. Why don't we worry about the orbits inside here?
That's
Not
your-
really,
Because you're in the black holes, it doesn't matter what you're doing.
Good luck.
We're only worried about the orbits around the stationary black.
Or if you're on the, if it's a rotating black hole, you can still exit. If you're.
If
like,
you're
if
in,
you're only the
there's
first
gonna be,
one.
there's gonna be 2 event horizons. There's gonna be a screwed up singular, a very screwed up singular.
Interesting idea. What if there's a planet orbiting just within it, like within the first event horizon? Is that?
That'd be possible. And that.
And then you could leave.
Well, to leave, you have to do something called the Penrose process. And that, the Penrose process would be hard. And I think for a whole solar system or a whole planet.
I don't mean the planet leave. I mean, you can be on the planet, get on a ship and then leave.
Yes, you could, but you have to do what's called the Penrose process. We won't talk about that.
It's a lot of paperwork. You have to like fill out.
No, when you.
Bureaucracy.
You have to deal with taxes and stuff like that, you
Oh.
know, the tax rate inside the event horizon is different from the tax rate outside there.
They
No.
would, you gotta expect.
You can't go table.
Well,
No, internet
it's like
access
black
is awful.
holes, Taxes are gonna be high.
Okay.
Your universal passport.
You have to get.
It's inoperable inside. You have to get like an exterior